Look up at the night sky tonight. That vast, star-studded canvas, it feels immense, doesn't it?
It really does.
But here's the truly mind-bending truth. What you're actually seeing, the stars, the galaxies, that glittering cosmic tapestry, that's less than 5% of what's truly out there.
Less than 5%. It's staggering.
The rest, it's completely invisible to us, shrouded in mystery, and yet it shapes absolutely everything we observe. Okay, let's unpack this.
Indeed. It's a profound cosmic riddle. The vast majority of our universe remains unseen. We're talking about concepts like dark matter and dark energy.
Okay.
These are the hidden forces that play a fundamental, almost architectural role in shaping the universe, even though they remain beyond our direct observation for now.
And that's precisely our mission for this deep dive. We're going on an awe-inspiring journey through the cosmos, guiding you from the explosive birth of our universe through its grand narrative, all the way to the cutting edge of cosmic theories. We'll uncover surprising facts about these unseen forces and the incredible structures that literally bind our reality together. Prepare to look at the night sky a little differently after this.
Definitely.
So let's dive into the very fabric of reality, the basic physics that governs the universe. Here on Earth, gravity keeps our feet firmly on the ground. It's familiar, right?
Sure, we experience it every day.
But out in the cosmos, its role is far more dramatic, dictating the grand ballet of galaxies and the very structure of space itself. Think of it less as a pull and more like this. Imagine space-time is a giant, stretched-out trampoline.
Okay.
If you place a massive object like a bowling ball on it, it creates a deep dip, right? And anything nearby would just roll towards it.
Right, it follows the curve.
Exactly. That's a simple but powerful way to visualize gravity on a cosmic scale.
What's fascinating here is that this analogy really nails the concept of space-time curvature. Massive objects, stars, galaxies, entire clusters literally warp the fabric of space and time around them.
They make dents in the trampoline.
Sort of, yeah. This is the realm of Einstein's general relativity, where what we perceive as gravity isn't some invisible rope pulling things,
Right.
but rather objects simply following the curves and dips in space-time that mass has created.
And it's this very dynamic, flexible fabric that ties into the universe's most astounding revelation, its expansion. It's wild to think that Albert Einstein initially struggled with this idea, you know?
Yeah, he added the cosmological constant.
Right, just to force a static universe model.
Well,
He later called that particular fix his greatest mistake after Edwin Hubble definitively discovered the universe was, in fact, expanding.
yes, and this is crucial to understand. It's not galaxies moving through space like cars on a road.
Right.
It's space itself expanding, carrying the galaxies along with it further and further apart.
So space is stretching.
Exactly.
Okay.
This expansion is why light from distant galaxies appears redshifted, meaning its wavelength is stretched, shifting it towards the red end of the spectrum.
Okay.
Hubble's law precisely relates a galaxy's recession velocity, how fast it's moving away, to its distance.
Makes sense.
What's truly puzzling today, however, is the Hubble tension. We have this significant, persistent disagreement
Between what?
between how fast we measure the universe expanding today using things like supernovae versus what our models predict based on observations of the early universe from the cosmic microwave background.
That sounds problematic. Not just a small measurement error.
No, precisely. It's a highly statistically significant disagreement. It's not just a tiny discrepancy. It's a profound puzzle. It points to a potential crack in our fundamental understanding of the universe.
Wow.
Yeah, possibly hinting at entirely new physics waiting to be discovered.
That's incredible. A potential hidden layer to reality right there. And speaking of vastness, let's talk about the sheer expanse. There's a big difference between the observable universe, what we can actually see from Earth, and the total universe, right?
Absolutely. The total universe is likely vastly larger than what we can currently detect, perhaps even infinite. We just don't know.
And it's not like a big sphere with us in the middle.
No, that's a common misconception.
Yeah.
And our understanding of this cosmic structure has truly revolutionized over time. I mean, think about it. From ancient sky maps
Right.
to early astronomy, we've come an immense distance. Key milestones in modern astrophysics include discovering globular clusters. These are ancient spherical systems with like hundreds of thousands to millions of stars,
Wow.
often found orbiting in galactic halos. And also the widespread use of Hertzsprung-Russell diagrams. They helped us figure out star properties, stellar evolution, even distances.
In connecting those early observations to our modern understanding, we can now piece together how our own Milky Way galaxy formed. You mentioned different types of stars. Halo disk stars.
Yeah, halo, thick disk, thin disk stars.
They aren't just random. They actually suggest that the primordial gas that eventually coalesced into these regions must have had unique origins, different histories.
Exactly. And it's fascinating how subtle chemical markers can tell us so much. Like deuterium, that's a heavy isotope of hydrogen. It was created only in the Big Bang and gets used up inside stars. So measuring it acts like a cosmic clock, helping us track gas consumption and star formation rates throughout our galaxy's long history.
So we've seen how the universe stretches out into unimaginable distances and how our own galaxy came to be. But how did it all begin? Let's rewind the cosmic clock way back.
Right, let's zoom into the very origins of matter itself, starting with the Big Bang. Very soon after that singular event, as the universe cooled below like 2 trillion degrees.
2 trillion.
Yeah, incredibly hot. Primordial quarks and leptons, the fundamental particles, began to form protons and neutrons from what was essentially a quark-gluon plasma.
Okay, a particle soup.
Pretty much. Then, just a few minutes later, in a process we call Big Bang nucleosynthesis.
Right.
These protons and neutrons fuse to create the lightest elements, hydrogen, helium, and tiny traces of lithium and beryllium.
So the very first elements.
Exactly. This explosive forging process concluded relatively quickly after about 20 minutes, just because the universe was cooling and expanding so rapidly.
So if the Big Bang only made the lightest elements, where did all the heavier stuff come from? Like the carbon that makes up you and me, or the oxygen we breathe.
Ah, that's the profound part. Crucially, heavier elements like carbon, oxygen, iron, all that stuff weren't formed in significant amounts during this initial Big Bang phase.
Okay, so where then?
They were forged much, much later. Inside the furnaces of stars through nuclear fusion, we call that stellar nucleosynthesis.
So stars are element factories.
Absolutely. And then these heavier elements get released back into the interstellar medium during colossal stellar explosions, supernovae.
Right, supernova nucleosynthesis.
Exactly. They enrich the cosmic gas. Stars themselves then condense from these molecular clouds, which are primarily hydrogen and helium, but now they have a few percent of these heavier elements mixed in from previous stellar generations.
So this means that every atom of carbon in your body, every atom of oxygen in the air, it was forged in the heart of a star that lived and died billions of years ago.
That's right.
You are, quite literally, stardust. That's a truly humbling thought.
It really puts things in perspective.
Now, here's where it gets really interesting. We've talked about the matter we can see, the 5%. But what about the invisible architect that truly shapes the cosmos? Dark matter.
Yes, one of the universe's greatest, most persistent mysteries.
Let's get into it. What is it? And maybe, what isn't it?
Okay, good place to start. It is not stars, planets, dust, or even regular black holes made from collapsed stars. It doesn't emit, absorb, or reflect light.
Which is why it's dark.
Precisely. That's why we can't see it directly. In essence, it seems to only interact through gravity.
Okay.
You could say dark matter is kind of like the wind invisible, right?
Mm-hmm.
But you can see its effect on the leaves.
Ah, I like that.
On a cosmic scale, we see its profound effects on galaxies and galaxy clusters, like these invisible cosmic currents shaping everything.
So if it's invisible, if it doesn't interact with light, why are we so sure it exists? What's the compelling evidence?
Well, there are several key independent lines of evidence that all point towards it. It's not just one thing. First, there's the galaxy rotation problem.
Okay, what's that?
When astronomers measure how fast stars orbit the centers of galaxies, they consistently find that stars way out at the edges are moving much, much faster than the visible matter alone can explain gravitationally.
Too fast to stay in orbit.
Exactly. It strongly suggests there's a huge amount of unseen mass dark matter, providing the extra gravitational pull needed to hold those stars in orbit. Without it, the galaxy should just fly apart.
Okay, that makes sense. Like invisible glue. What else?
Second, gravitational lensing. Light from distant galaxies gets bent, warped, as it passes through massive galaxy clusters on its way to us.
Like a lens focusing light.
Sort of, yeah. But the amount of bending we see is much more dramatic than the visible mass of those clusters can account for. This extra warping indicates the presence of substantial unseen gravitational sources, which we attribute to dark matter.
Okay, so distorted light gives it away.
Yeah.
Anything else?
And third, the cosmic microwave background, or CMB. This is that ancient light from the early universe, less than about 500,000 years old.
The afterglow of the Big Bang.
Pretty much. The patterns, the tiny temperature fluctuations in the CMB, reveal the precise conditions of the early cosmos. And to explain those patterns, specifically the sound waves that traveled through that primordial soup,
Uh-huh.
you need a specific amount and type of dark matter. It provides a unified explanation that alternative theories like modified Newtonian dynamics or MOND really struggle to match across all these different scales from galaxies to clusters to the CMB.
That's incredible. It's like we're seeing its footprints everywhere, even if we can't see the creature itself. So how much of this invisible stuff is actually out there?
The composition of the universe is truly surprising, maybe even humbling. Roughly 27% of the universe's total mass energy budget is dark matter.
27%.
Yeah. For comparison, the normal matter, the stuff we see, stars, planets, us, makes up only about 5%.
Just 5%. What's the rest then?
The rest, a staggering 68%, is believed to be dark energy. That's another, even more mysterious component driving the accelerating expansion of the universe. But that's maybe a whole other deep dive.
Wow. Okay, so 27% dark matter, 5% normal matter. So what are the leading theories about what dark matter might actually be? What kind of particle?
Right, so the scientific community has several leading candidates, all hypothetical at this point. The most popular for a long time have been WIMP,
War WIMPs.
weakly interacting massive particles. These would be new, heavy particles that interact very rarely with normal matter, only through gravity and maybe the weak nuclear force.
Okay.
Any other candidates?
Then there are axions. These are hypothetical ultralight particles, very different from WIMPs. And also sterile neutrinos.
Sterile neutrinos.
Yeah, they're fascinating because their existence could link to grander theories of physics, maybe suggesting entirely new scales of reality way beyond what our current standard model describes. Neutrino physics keeps surprising us.
It's also theoretical, though. How are scientists actually looking for this stuff? You can't just point a telescope, right?
Right, far from it. The search is multifaceted and incredibly challenging. Scientists are running direct detection experiments deep underground.
To shield them from cosmic rays and other background noise. They're basically building detectors with extremely sensitive materials, hoping to see one of those incredibly rare interactions when a WIMP bumps into an atomic nucleus.
Wow, looking for a needle in a haystack.
A very, very big haystack. Then there are collider searches, like at the Large Hadron Collider, the LHC.
Okay.
They smash particles together at enormous energies, looking for subtle signatures, like missing energy, that might indicate dark matter particles were produced and flew away undetected.
And anything else?
And finally, astrophysical surveys use powerful telescopes for indirect searches. They look for the byproducts of dark matter particles annihilating each other out in space, like excess gamma rays or cosmic rays coming from dense regions like the center of our galaxy.
So what does this all mean? Why does this invisible stuff, this dark matter, matter so much? Why spend all this effort looking for it?
Its importance really cannot be overstated.
Yeah.
Fundamentally, without dark matter, galaxies as we know them simply wouldn't have formed.
Really? How so?
It acts as an invisible scaffold. Its gravity pulled normal matter together in the early universe, providing the gravitational wells necessary for gas to collapse and form the first stars and galaxies. It holds together the large-scale structure of the cosmic web we see today.
So it's the hidden backbone of the universe?
Exactly. Without it, the universe would look vastly different, maybe even devoid of complex structures like us.
It truly is amazing how much we've learned, and yet how much is still hidden. This brings us to humanity's relentless drive to see the unseen, to understand the cosmos. Our curiosity has led to some incredible innovations over the centuries.
Oh, absolutely. Our quest to observe the universe has driven an incredible evolution in technology. Think about early refracting telescopes, like the one Giovanni Cassini used back in 1675 to spot the gap in Saturn's rings, the Cassini division.
Right, simple lenses.
Simple but revolutionary for the time. Modern telescopes now ingeniously use both lenses and mirrors, catadioptric designs, for vastly superior views, and for the really huge ground-based telescopes. Segmented mirrors have become key. You can't really make a single perfect mirror much bigger than about, say, 8.4 meters across, so they build them out of smaller segments fitted together.
Clever.
And of course, getting above Earth's blurry atmosphere with space telescopes like Hubble.
Hubble changed everything.
It really did. It helped nail down the Hubble constant, for example. And now, the James Webb Space Telescope, JWST, is pushing boundaries even further, confirming those expansion rate measurements and peering deeper into the early universe than ever before.
But we don't just use visible light anymore, do we? How else are we probing the universe?
Correct. We use the entire electromagnetic spectrum and more. Radio astronomy, for instance, with giant dishes like the Parkes telescope in Australia, was crucial even back in the 60s, supporting early deep space missions like Mariner 2 to Venus.
And now we have things like gravitational waves.
Exactly. We're now detecting gravitational waves, these ripples in space-time itself. It's like the universe is humming. We use things called pulsar timing arrays.
Pulsars, the spinning stars.
Yeah, incredibly precise cosmic clocks. By timing their pulses across the galaxy, we can detect these super subtle, long wavelength gravitational waves passing through. Some might even be echoes from the Big Bang itself.
That's mind-boggling, using the galaxy as a detector.
Yeah.
What about actually going there? Sending probes?
And let's not forget deep space probes. NASA, ESA, other agencies. They've had this spectacular era of solar system exploration. We've sent spacecraft to fly by, orbit, land on, or even rove across every planet.
Every planet.
Every planet, plus dwarf planets like Pluto with New Horizons. Think of Cassini-Huygens at Saturn and Titan, revealing incredible details. And right now, the Mars 2020 Perseverance rover is actively searching for signs of ancient Martian life.
Looking for fossils.
Essentially, yeah, signs of past microbial life, and it's collecting samples, drilling cores, caching them for a potential future mission to bring back to Earth.
Incredible. With all this exploration, all this looking out there, it's impossible not to ask the big question. Is anyone else out there? Are we alone?
Ugh, the search for extraterrestrial life. It's a truly compelling driving force in modern astronomy and astrobiology. We're constantly discovering exoplanets, planets outside our solar system.
Thousands of them now, right?
Thousands confirmed, yes. And many are in potential Goldilocks zones, not too hot, not too cold, where conditions might be just right for liquid water on the surface. And maybe, just maybe, life as we know it.
And we know life can exist in tough places too.
Exactly. The existence of extremophiles here on Earth, organisms thriving in incredibly harsh environments, like boiling volcanic vents, deep under ice sheets, high radiation. It dramatically expands our understanding of where life could potentially exist. Maybe not just on Earth-like planets, but perhaps on icy moons like Jupiter's Europa or Saturn's Enceladus, which seem to have subsurface oceans.
So we're looking for planets in the right zones. And we know life can be pretty hardy. But how do you actually detect life on a distant world, maybe light years away?
That's the million-dollar question, isn't it? The challenge is identifying biosignatures. These are indicators, maybe gases in an exoplanet's atmosphere like methane, ozone, or oxygen, that might suggest the presence of life.
Might suggest.
Well, yeah, because while here on Earth, life, specifically photosynthesis, is the dominant source of oxygen,
Right.
studies show that you can also produce ozone and molecular oxygen non-biologically. For instance, if intense UV light from the star breaks apart carbon dioxide molecules, so detecting oxygen alone isn't necessarily proof of life.
Ah, okay. So it's complicated.
Yeah.
False positives are possible.
Very possible. We really need multiple lines of evidence, multiple potential biosignatures, ideally in context with what we know about the planet and its star, before we can be confident. It's a huge challenge.
It really puts our own existence into such a vast cosmic perspective. Let's maybe take a quick run through the universe's timeline just to see where Earth and life and us fit in.
Okay, the grand sweep. The Big Bang is estimated around 13.8 billion years ago, give or take.
Yeah.
The first stars, these massive short-lived population 3 stars, and the first quasars started lighting up the young universe maybe 200 million years after that.
Pretty quickly, cosmically speaking.
Relatively, yeah. Our own Milky Way galaxy began forming pretty early too, maybe around 13 billion years ago, with its halo and thick disk taking shape within the first billion years or so.
And our solar system?
That's a relative newcomer, formed about 4.6 billion years ago from a collapsing cloud of gas and dust.
And life on Earth?
The first life seems to have emerged pretty early in Earth's history, around 3.5 billion years ago. Some evidence hints it might even be older, maybe more than 3.8 billion years.
Wow, life got started fast.
It seems so. Then, much later came key evolutionary milestones. Oxygen building up in the atmosphere thanks to cyanobacteria, the first complex animals, fish, land plants. Placental mammals, like us, our ancestors, really diversified after the extinction of the non-avian dinosaurs, starting around 66 million years ago.
And humans, modern humans.
Anatomically modern humans, Homo sapiens, maybe around 300,000 years ago, a blink of an eye in cosmic time.
Absolutely tiny. And within that enormous cosmic clock, human ingenuity has made some truly monumental leaps, especially recently.
Incredibly recently, yes. Think about our space exploration efforts. NASA's first successful planetary flyby, Mariner 2 to Venus, was only in 1962.
Just 60-odd years ago.
Exactly. Then the Apollo missions, landing humans on the moon. And the continuous development of these incredibly advanced rovers like Curiosity and Perseverance on Mars, plus probes that have visited every planet and beyond. It's a testament to human curiosity and capability in a very short span.
All this knowledge, all these discoveries, they naturally lead us to ponder some truly mind-bending theories. What about that idea that challenges our very perception of where we are? The theory that our entire universe might be inside a black hole.
Ah, yes, that one. It's definitely one of the more intriguing and, mind-bending cosmological hypotheses out there. The idea that our observable universe could be the interior of a black hole existing in some larger parent universe, or maybe an inside-out black hole, a white hole.
Wait, our entire universe? That sounds pretty wild. What are the parallels? Why would scientists even consider that?
Well, there are some fascinating conceptual parallels, though it's highly speculative, of course. Both black holes, as seen from the outside, and our expanding universe have a horizon, a boundary beyond which we can't see or receive information.
The event horizon for a black hole and the cosmic horizon for us.
Exactly. Both are also, on the largest scales, roughly spherically symmetric, and both involve expansion or contraction in some sense, the singularity inside a black hole, the expansion of our universe. Some models propose that the formation of a black hole could lead to the creation of a new universe inside it, or perhaps on the other side, appearing as a white hole expansion.
So a new universe could theoretically be born from every black hole. That's quite a cosmic recycling program. And you mentioned rotating black holes earlier. Does that fit in?
It potentially does. Some specific rotating black hole cosmology theories propose that the effects of frame dragging, the way a massive spinning object twists space-time around it,
Uh-huh.
inside a rotating black hole could actually mimic the gravitational effects we attribute to dark matter, particularly on galaxy rotation curves. So maybe we don't need exotic dark matter particles if we live inside the right kind of spinning black hole universe.
So that could explain the fast-spinning galaxies.
It's a possible explanation within that framework, yes. However, current large-scale observations of the universe tend to favor isotropy, meaning it looks roughly the same in all directions with no preferred axis of rotation. If that holds true, then if we are in a black hole, it would likely have to be a non-rotating or very slowly rotating one, which wouldn't easily explain dark matter effects via frame dragging. So it's complex, still very much debated.
A captivating idea, but lots of hurdles still.
Definitely captivating. Lots of hurdles.
Well, as we wrap up this deep dive, it's clear we've only just scratched the surface, really. We've journeyed from the universe's explosive birth, explored the fundamental forces, uncovered the profound mysteries of dark matter, dark energy, these unseen components, and marveled at humanity's incredible, persistent drive to understand it all.
And it really raises an important question, or maybe reinforces one. For all our incredible telescopes and probes, for all the elegant theories, the simple fact is the vast majority of the universe remains invisible, unknown to us. The implications of dark matter in particular are just profound. It shapes everything we see, everything we are.
We may never fully see dark matter in the way we see stars, but maybe, like those invisible forces that shape our own lives, gravity holding us down, the wind we feel but don't see its invisible hand is everywhere,
Binding the universe together.
binding the universe and our story together. So keep looking up at the night sky, keep wondering, because there is so much more out there than meets the eye.